Okay, so let us start. So last time we, for no apparent reason, started talking about simplicial sets. So just a reminder what the simplicial set was. There was this category of simplices where objects are called like n, which is the ordered set 0 less than 1 less than etc. less than n. And morphisms are order preserving maps. And then a simplicial set is a functor going from delta up to the category of sets. And we shall not use it for, say, topological applications, but rather as a combinatorial gadget to encode either groups or Hopf algebras. So let me now start talking about some special type of these simplicial sets, namely nerves. So what do? Let us start, say, with a monoid. Ordinary monoid, a set with a operation. In the end, I want it to be a group, but for the moment it's okay to, or maybe better to keep it a monoid. And then there is a simplicial set called the nerve. The one that I'm going to use is B of M. Now this bullet will stand for like this. I'm talking about Bm applied to that n, and the standard notation is to put that n as a subscript. But anyway, what is this guy? So it's just n copies of M. How should one imagine it? So let's take, let me draw something for n equal to, let's see how many. Say this is n equal to 4. So you imagine this is like 0, 1, 2, 3, 4. These are those numbers. And now for every edge that I drew, we put there one copy of M. It means that an element in B4 of M would be like probably here M1, M2, M3, M4. Where are those MIs are in M? Okay, so that's what it does with objects. And I should say how is it functorial? Say, let me take something like this. So this is now for n equal to 3. Let's have a morphism in this category. I don't know, say this one. Sorry. That. So it should be an order preserving map. That's one. Certainly. And now I need to have a map going from this B4 to B3. So what do? When you see here, like this guy is expanded to two slots. So what do? You just multiply everybody who's in this expansion. These are just 2. And I'll write just M1, M2. Now, maybe a little wording, it doesn't matter in the end, but I think people would often write it more like M2 times M1 for the reasons that that's the convention for composition of arrows, that you write it, the composition in the opposite order. But I'll keep it this way because for me it's easier to do it that way. Now, here, this thing is collapsed into nothing, so you just put the 1 here. For every edge which is collapsed, you put 1. This guy is, well, mapped here, so you just don't have to multiply anything, it's just M3. And this M4 doesn't get a word, it just disappears because there is nobody being mapped there. So a better description is probably to say that you would see this Bn as all functors going from this stuff seen as a category to M seen as a category with a single object, but this description is perfectly okay for us. And, okay. this is one thing. Now we're going to have a proposition which says that, let's first start with a remark, is that we can reconstruct M back from its nerve. Now, how is it? Well, you see, we already have the product is basically what's happening here. So for that, how do we do it? So let's take let's put it this way: that M itself is just B1 of M. Now now we can obtain a bijection between B2 of M to M times M. How does it work for that? Just imagine that there are two natural maps going to B1M, which is given by one of them is this. Just put it like that, and that will only remember this M1 from here, right? So if here we have M1 and M2, then this thing is contravariant functor, and it will remember exactly this M1, and the same stuff is happening for this map. So there is M2. So we have these two maps going from B2M to B1M and B1M, given just simply by the simplicity structure. And it happens that, well, this map going to the product is actually bijection because it's the nerve of something. So for the nerve of something, that's true. And now the product how does one get it? Well, for that, we have this third possible reasonable map. And when we take this morphism in the simplex category, then this is going now again from B2M to B1M. What does it do? We take M1, M2, and here we get M1, M2. And probably if it's a monoid, I should also say who is the unit. So the unit somehow that's what's happening here, more or less. So we take B0 of M, who is just a point. There is nothing here, or there's a single element. And now we take this unique morphism going from 1 to 0, which is, well, everybody's map to this single point. And now it's a contravariant functor, so it should send this single point. That should give us a map going from B0M to B1M. In other words, from this point, from the single element, is mapped into M, and that's the unit. Okay, so nothing surprising. So one can simply say that this nerve thing is simply our monoid with all possible products already written down, right? That you take a chain of elements of your monoid, and now decide whom of them you're going to multiply. Maybe sometimes you want to insert some unit, and maybe sometimes you want to delete some element. So it's something like this. Or if you wish, you probably don't, but I know I can write it this way, that what we proved is this little proposition that we have it's actually a functor going from monoids to Simplicial sets. So this B thing, Simplicial sets, is a functor, certainly. And what this basically shows that it's a fully faithful functor. There is like an embedding of categories. But I will not need these fancy words. For me, what's enough is that we can reconstruct back the nerve from, the monoid from its nerve. That all the structure is simply there. Okay, now another proposition which we're actually going to use, unlike this one. The question is now whether we can, if somebody gives you a Simplicial set, whether you can recognize that it's the nerve of something. That there are Simplicial sets who are not nerves of any monoids, and there is now we need a proposition. So how to recognize the nerves of monoids. So let's suppose that it says something like this. So let X be a Simplicial set. Now let's consider these maps. Which are given, okay, they go from x k plus L to xk times xl. And what are these maps? We already saw that for k and L equal to 1. So let me tell you what the thing is. So we consider the map going from k to n. So this will then induce a map going from xn to xk, and another one L to n, which then induces, since x is contravariant, it will induce something from xn to xl, and we take the product of these two maps. So that's the product. But who are these things? So that's what I did draw. Like that. So this guy is putting those bullets at the beginning, and that guy is putting them at the end. So this first map is the thing, and the second map is that thing. So this is 1, 2, 3 plus 2. This is 3. And this is 2. Okay, let's do this. Now, as you can imagine, if this X is actually the nerve of a monoid, so what happens? Then monoid is simply for each edge, you have a copy of M. So it means that this map is actually a bijection. Right? Because like what is induced from here, we simply remember the first part of the thing, then you remember the second part. And the proposition says that it's actually if and only if. So you probably should write V maps. So then X is the nerve, a monoid, and that monoid is then necessarily X1 if and only if those maps are bijections for every K and I. So let's start to prove it. So one direction should be very easy. The statement that if X is actually is the nerve of something, then this is true. So if X is B M, then this whatever. That thing is simply M power L goes to M power K times M power L, which happens to be bijection, right? Now, so if those things are bijections, then simply by repeatedly using that stuff, so say decomposing those numbers to smaller and smaller, then necessarily X n is, well, in bijection with X1 power n, right? Where if you wish, this thing is given by, let me draw it like that. When you consider now n maps from an edge to our n. So this is 3, and these are like 3 copies of 1. And for each of those edges, you do this, and then you get a bijection. That's what we suppose in the end, right? And then what? First I should say what is the product? So define n times m to m, where this m is by definition x1. And how do we do it? Well, exactly as you can imagine. We have this. We're going from x2, sorry, to x1. So we want to go this way, which is n times m. This is m. We go there this way. Now that product is associative. Why is it associative? Just consider what's happening with x3. So we take that thing. So let's go from x3, who is m cubed, to x1, who is m. How do we go there? Well, just in this way. And now you can easily verify that the map that we get here from m cubed to m can be obtained simply by applying the product first on these two and then multiplying with that guy, or by applying it first there and then multiplying with this guy. It's simply the composition of two morphisms. So that's associativity comes from here. I should still say who's the unit. Is given as before, so this x0 is just a point. Maybe it's a good idea to think about why it's actually a point. So, and we would like to go from here to m, to x1 with m to obtain the unit, and it's obtained in this way. Okay, cool. So that gives us this unit. Now you easily verify that this unit is actually a unit for that product. And then you easily verify that just by understanding what's happening with this couple of pictures, those smallest pictures, we can now understand what's happening for arbitrary morphism in this simplex category, because they can be obtained by composing these. So let's call this the end of the proof. And yeah, okay. The final remark is that when M is actually a group, M equal G so then there is another construction of the nerve of a group, which is possibly simpler. I don't know, it depends on your taste. So what we can do, we can construct some other simplicial set. E.g., which is simply that E and G is this time G power n plus 1. So we're not writing anything on edges, but rather on those vertices, on those bullets. So one can say that this guy is the same as all maps from this set n into G. That's the set containing 0, 1 up to n. We map it to G, so we obtain like this set. And that's certainly contravariantly functorial in this first slot, just because it's the maps from something to somewhere. So just to draw it, imagine something. I would write something like G0, G1, G2, G3, and that's an element in E3G. Something like this. So you see, here G might be just any set. Nothing is used about the group, or there is no multiplication ever used in definition of this simplicity set. But from here, there is now we can now just say that BG is equal to EG when we mod out this guy by the diagonal action of G. Normally people write this action on the right, and it's a better way to write it, but in my notes finally things worked better if this action is on the left, so sorry for doing it that way. Of course it doesn't matter. So this is the action by left multiplication of everybody. So it means that I take somebody some age and multiply everybody by the same age. And what is the map? Well, the map is what is the isomorphism between this and that? It's simply, I only remember how to go from G0 to G1. So I only remember the difference of those two things. And of course, I never remember which way. So it would be G0 inverse G1 that I would put on this edge, and then G1 inverse G2, and G2 inverse G3. So you see, so it's somehow, that is the thing by which we have to multiply G0 to obtain G1, etc. So from here to there, we have to go by multiplying with this guy, etc. And that certainly shows that actually this thing is a bijection and isomorphism and everything. You see, it's only, we have only free, when you when you want to go from here to there, the only freedom is in choosing G0. Once that is chosen, then everybody else is clearly defined. Okay, so something like that. Now, yes, sure, like this, well, it's totally irrelevant for this class, but one should probably still say it, that this EG, that's a combinatorial simplicial model for the classifying space of principal G bundles. This one is the classifying space of the simplicial of principal G bundles. So that's when you interpret simplices as actual, those abstract simplices as actual simplices, and so you build that space out of that. That's what you would get. But well, here in this class, everything is just combinatorics, so we don't need it. Yeah, but what do we actually want to do? We want to construct Hopf algebras. You know, everybody forgot, at least I forgot, but that's why I started talking about this stuff. And so what is the idea behind? So somehow Hopf algebra is supposed to be some kind of non-commutative group, non-commutative in somehow being in non-commutative world. That it's no longer a set, it's some kind of very non-commutative object, but it's supposed to be some sort of generalization of a group. Now, we rephrased what, for the moment, only monoids, but well, groups are monoids with invertible elements, so that's not a problem. So we replaced monoids with simplicial sets. Now we're going to do a kind of the same thing with Hopf algebras, and from there we will finally construct all those Hopf algebras. So now. So where we're heading is we want to construct the nerve of a bi-algebra. Because bi-algebra is the thing which is going to replace monoids, and then when there is actually an antipode, then it's going to be a Hopf algebra. So for that we need some couple of definitions. So first of all, say a simplicial object in a category C, as you might imagine, that we're just replacing sets with this category is a functor going from delta up to C. It's easy enough. Let's now have a look at what we can do. So let's start in this way. So one thing that can be easily mimicked with this construction of the nerve is that if, suppose now that C is a monoidal category, and A is a monoid in this monoidal category, or what I call an algebra. Algebra, maybe a monoid. In C, that's not quite enough to construct a nerve. We need a little bit more. We just need to suppose that this algebra is augmented. And so it's an epsilon going from A to 1. Is an augmentation. Is a morphism of algebras, or what is called an augmentation. So then there is something which is not really called a nerve, but it can be called like that, but it's mostly called the bar construction. So the of A. So it's some B A, who is a simplicial object in the C, and it's constructed exactly the same way as the nerve of a monoid. So what it is? So B and A is simply the nth power of A, and I should tell you now in what sense it's a simplicial object. So let me draw a picture. Not sure whether I'll manage to draw the same picture as before. So what's happening here? So here, n is equal to 4. So here we have A tensor power 4. I'll draw 4 A's. For each edge there is one A. Now this is 3. A. Let's now take a morphism going from 3 to 4, any morphism or one that I'm going to draw. Then I should tell you what I should give you a map going from this A power 4 to A power 3. And I hope it's the same morphism as I had before. So what do we do? Well, we try to find the chalk. So what's happening here? You see, here we have two A's. So what do? We just multiply them. There is this map going from A tensor A to A. So here, in this way, we apply the product in A. Now, this thing is collapsed to nothing, so here we just put there this one thingy. Here there is a single A, nothing's happening here. We simply keep this identity. And now, at this point, it gets finally clear why we need this epsilon. Because when there is an edge which is not in the image of anybody. We need to get rid of that stuff. The only way how to get rid of stuff is to put epsilon here. So epsilon just collapses this to the unit object, so just then disappears. Or if you wish, morally, if I draw it, something like A1 tensor, A2 tensor, A3 tensor, A4, then what we are getting here is A1, A2, tensor 1, tensor A3, and simply times epsilon of A4. This just doesn't make any sense in an arbitrary category. There are no elements in there, but this is some at least possibly a more understandable way of writing of that stuff. Okay, so this is this bar construction. I guess it's clear that this indeed is a functor going from delta up to C, just that stuff. And yeah.
What about the associative structure?
Okay, you mean this monoidal category thing? I just now imagine that every monoidal category is strict.
Okay.
Or because that was somehow a message that that I try to convey to you, that it doesn't matter, that all those parentheses, they disappear always. But you are somehow right that I should, when I write this, then I should probably choose some bracketing, because this doesn't make sense as it's written. But then all possible parenthesizations of those things are uniquely or canonically isomorphic. So it doesn't matter. I just stopped writing those parentheses because they are really annoying. Okay. And now you would expect this kind of proposition that, or maybe, I don't know, you wouldn't expect it, but you would expect the worst from me. So in particular, this kind of proposition, which would say that what would that say? Yes.
Just a notation. So the BA is called the bar construction of A.
Yeah, the bar construction of A, or you can call it the nerve of A. Doesn't matter. So the proposition now would say that we can actually now recognize nerves of those augmented algebras, and that one can reconstruct the algebra from its bar construction. Just it's not true. So remark. So one cannot So where's the problem? So, okay, A as such, as an object, certainly can be reconstructed. It's just B1 of A. So it starts very well, but then we would need to, this is okay, but no way of reconstructing this isomorphism between B2 of A and A tensor A. One just cannot do that. Strange, maybe it's strange, but okay. You see somehow what's happening, how we're doing it before. So we were considering those maps either this way or that way. So which then gives us a map going from B2A to, well, B1A, which is A, another map going to A. That's fine. We still do have these maps. But there is now no way how to say that we have a map going from B to A tensor A. We have a map going from B to A tensor, B to A tensor A if you really want. But that's the best thing we can write. No, just doesn't work. Right, so we have those two maps, but there is no way how to combine them to a map going this way. Yep.
A very stupid question, but B2A is.
Okay, but say somebody secretly takes an A, creates this simplicial object, gives you this simplicial object. Now you're supposed to just reconstruct who was that algebra A, and you fail.
Okay.
You find A itself as an object, but there is no way for you how to find the product there.
Okay.
Possibly it might be a good exercise to look for examples just when those A's are actual algebras, when the C is the category of vector spaces. It cannot be done. That's because this A is not a good replacement of a monoid in sets. A good replacement of a monoid in sets is actually a bialgebra. So what we're going to do, I'll just write it here. So we take a H, which is a bialgebra in C, and now the C, to even be able to talk about bialgebras, the C has to be a braided monoidal category. The bialgebra in C is the same as an algebra in the category of C. In the category of C coalgebras, this is a monoidal category. And once we start doing that, then all of a sudden, this is no longer such a huge problem. So, because then, well, I'll do it after a break, but just to see what's happening. So then all those B and A's are here in C coalg. So that means that they are coalgebras, those things. And so it makes sense to say that we go from B and A, we can go to A, and we have another map going to A, just given by these two maps. So then we can take the tensor product of those and go to the tensor product of these. Right, so that's fine. And it's a coalgebra, so this bad stuff, or sorry, it's n is equal to 2, right? 2. So it's B to A. Now going here with the coproduct. So all of a sudden, this makes sense.
So A is H, right?
A is H, yes. Or, I don't know, like invisible roof or something. Okay, but so let's talk about it after the break. Okay, so shall we start again?
This is just. I don't know.
Yes, so there was a question that how comes that this thing doesn't work when it works for ordinary monoids? How comes that we cannot reconstruct the algebra from its nerve when we can do it for monoids? And the thing is that, well, it's sort of obvious, but still, that in sets, that if M is somebody who's an object in sets, then it always comes with a natural coproduct, which is just the diagonal map. And in fact, that's also the unique co-associative coproduct you can prove. Maybe there will be an exercise that if you have a coalgebra in sets, then, well, there is a unique way how to make set to a coalgebra. It's just with this diagonal map. And so then we automatically have this. Right? So this tensor product is just a Cartesian product. And so that's what happens. So actually one can say that a monoid in sets is automatically a bialgebra. And in fact, the bialgebra in sets is the same thing as a monoid in sets. There is only one way how to put there that coproduct. Okay. I'm not sure whether it explained anything, but possibly. So, and what did I want to say? So that we have this proposition, or maybe let me write it again. Oh, it's written there, so I don't need to write it again. Okay. So propositions would say that a simplicial, say if C is a BMC, and X is a simplicial coalgebra in C, so simplicial object in the monoidal category C coalx. Then this thing is B of H for some bialgebra. H in C, well, if and only if. Now we have some maps as before, so it's going to be the same type of recognition principle as before. So if and only if the morphisms these are morphisms in C, which goes which way? So we can take x k plus L, then one can, it's a coalgebra, so we can apply the coproduct. We can go from here to xk tensor xl, but now from it's k plus L, k plus L, but now we know that from xk plus L we can go to xk, and also we can go to XL. So we just written how that morphism is obtained. It's just composition of these two. So if and only if these morphisms are isomorphisms of coalgebras in C. Yeah, and probably here I should probably add something, and if and only with this, and there is one more condition, which is just something one will forget. If it's x0 going to 1 in C, which is just epsilon, so just the counit on x0, if and only this is an isomorphism of coalgebras. So it's kind of exactly the same thing as we saw before, just now written, like as we saw just for monoids in sets, but just written in this more abstract way. There's maybe a little remark. You see, here I want this map to be an isomorphism of coalgebras. That's a slightly less trivial statement than it looks like, because The problem is that delta itself, in general, is not going to be a morphism of coalgebras. So this is not a morphism of coalgebras in general. Well, these things, they are morphism of coalgebras because X is a simplest object in coalgebras. But we still want these compositions now to forget enough of those bad things happening here to get an isomorphism of coalgebras to be, so that stuff should be compatible with the coproduct.
So if you start with my algebra, then this augmentation thing is just this epsilon.
Yeah, exactly. And let me sort of say finish that thing, or just a little bit addendum. So H is then reconstructive from this X as what? H is just X1, and the product H tensor H to H. So what is it? This is X1 tensor X1, who is isomorphic to X2. Here we can go to X1 with this favorite picture that we have 2 and 1, and the map goes this way. That's exactly what we were doing. Yeah, so this is equal to that thing. So this is the product that you obtain. And finally, the unit. So it should go from the unit object in C into H. Now this guy is, this is X1. This guy is, well, isomorphic to, that's what's written there with X0, and we know that's exactly what we had before, right? So the thing is to consider the unique map from 1 to 0. So here somehow life is wonderful. One can reconstruct back the bialgebra from its nerve. And we can recognize when a simplicial coalgebra is actually the nerve of something. And so what is the proof? It's the same thing as before. The same as for monoids. There is nothing different here. So if you, okay, maybe I can work, right? So where one would go, that first by iterating those isomorphisms, we can now say that this thing is equal to X1 tensor power n, and then, well, etc. Let's just stop here. Okay, so after this abstract thing, let's do another abstract thing. So finally, we get to construction of algebras. So how to construct. So what do we don't want to do? So somehow we want to mimic this construction where BG was EG mod G, and where this EG was very easy to construct because their EG was just a set, to say. So you want to do something like that. So how do we do it? Let me say write down the setup, and there will be a theorem. But so first, sort of EG. So we need to choose the category in which we work, and in the end, I want to use C for some other category. So let's start with D, who is a braided monoidal category. And now in place of a set G, from which we could construct this EG, let's start with a coalgebra. Now C is already used, so I don't know why I felt that Q is close to a coalgebra. So let Q in D be a coalgebra.
So the vector is D?
Sorry?
That's curly D?
In some sense. Yeah. So at first we actually only need it to be monoidal, but let's see. So then we can construct, I will call it this EQ. It's a simplicial object in D, and it's what is called the Khobar construction. Of Q, and it has a strange name, but it's something very simple. So what would it be? We really just imagine that there is one copy of Q at each vertex. So E and Q is by definition a Q power n plus 1 thing. And now I need to tell you what happens when we take a morphism. Right? So let's take the same one as always. So the difference now is I'm putting Qs on those vertices, right? Not on those edges, but on vertices. So this is a morphism going from 3 to 4. Right? And I should tell you how to go from E4Q to E3Q. So that stands a product of 5 Qs. Well, you do just the only thing you can possibly do. So what do you do here? You see, now we don't care anymore about those edges. We only care about those vertices. So here, this goes straight to Q. So here we just apply the identity on Q. Right? This poor vertex is not connecting to anybody. We have to kill it. We apply epsilon here. Now this rich vertex, on the other hand, is connected with 2 guys. So what do we do there? We apply the coproduct to go from Q to Q tensor Q. This guy is connected with just one thing. So we go with identity from this queue to that queue. And now this guy is again not connected to anybody, so we put there epsilon. Very easy. Sort of easier than before, because now you can ignore those edges. Now things are only happening with vertices. Now a little trouble now, or trouble, depends. Here we never used the fact that D is braided monoidal category. It's just monoidal category. It's perfectly okay. But the problem is that in a braided monoidal category, this EQ is not a simplicial coalgebra. So general Q, EQ, simplicial coalgebra. What do I mean by that? You know, this stuff, like tensor product or then also tensor power of coalgebras is a coalgebra in a braided monoidal category. So Q power n plus 1 is a coalgebra. Maybe a little reminder how it goes for n plus 1 equal to 2. The thing which is happening, we just take two Qs and then apply the coproduct in each of them. So this would be like the coproduct on Q tensor Q. The problem is that these maps are not morphisms of coalgebras. And the trouble is happening already for this delta. So delta from Q to Q tensor Q is a coalgebra morphism. So when is it happening? Maybe it's easier to think of in the ordinary words in terms of algebras. So when is A tensor A going to A, the product, when is it morphism of algebras? The problem is that you need to exchange things to do that. So your algebra has to be commutative. And this is exactly what's happening here. This is a coalgebra morphism if and only if Q is commutative. Okay, cool. So if you want to have a simplicial coalgebra, not just a simplicial object, but a simplicial coalgebra, we need to demand a bit more. We need to demand that this Q is co-commutative. Let's do it. Okay, now, so if Q co-commutative, so this implies EQ is simplicial in this category C co-algs, and it's not C but D, right? And where is it? Was there any C anywhere? I don't know. What is it? D. Okay, so we were able to construct some simplicial coalgebra. That's good, because we want to construct some simplicial coalgebra in the end. Because we want to construct a bialgebra, meaning we want to construct a Hopf algebra. But how do we get there? We cannot just use this EG thingy. We need to have this mod G thingy. So there is another ingredient. Or the EG is there, but now the analog of modding out by G should I just say it straight away? Possibly, I'll just say it straight away, and then maybe give you an example. So what we need a braided co-monoidal functor f going from D to some C. So here finally is the C, is again a braided monoidal category. So let's call it, I don't know, I need some, I guess traditionally there is no reasonable name, then people just call it admissible, right? So let's call it admissible. So such a thing is, say, Q admissible. That's just this notation made on spot, so there is no probably reasonable notation. Or so if what I want it to be something like this mod G. And what does mod G do here? It kills one G. That's what it's supposed to do. It goes from G power n plus 1 to G power n. So let me write down what it's supposed to be. So for every I know, X was already used somewhere. I don't know, U in V, objects in D. I want the following thing. That if I take U tensor Q tensor V, so there is one Q, and I want to make sure that applying F kills one Q. Now this is difficult to write it straight like that, but fortunately that Q can multiply itself. It's a coalgebra, so what we can do, we can go from here to just applying the coproduct on Q, and I should write F and identity on U and V, etc. So we can go to F U, Q, Q, V. And now our functor is co-monoidal. Co-monoidal means that we can split things. So there is a F is comonoidal. It means that we can do this. F U, Q, F, Q, V. So this is cool. This is what we can do. And now you see what's happening here. So there is one Q and one F. There are two Q and two Fs. And I want to imagine somehow that this F always kills that corresponding Q. And the way how to say it is to say that this composition is an isomorphism. Okay, that's the least comprehensible and most important part of that stuff. And there is still a little bit that one needs to do something with the unit. So which is the following. So if I take just F of Q, now I want to really imagine that this F exactly kills that Q. So this becomes the unit object. How do I do it? One can apply first the first epsilon on Q. So like F of epsilon, we go to F of 1 in D. Now our functor is comonoidal, so there is a F is comonoidal, so therefore we go to 1 in C, and again this composition is again required to be an isomorphism. Yeah, so this is bad enough, I understand. So let me maybe tell you some example. This example is really going to be about this EG mod G. So for D, I'll start with G, a group. D will be category of G sets. The sets with action of G, where the product is just the product, and the action is going to be diagonal action. For Q, I take just G with the left action. G acts on G by left. Multiplication, so that's what it should be. Now, what is this EQ? Well, it's just this EG, simply the same thing. But it's seen as a G set. So there is still, well, it's a set, it's G power n plus 1, but with action of G, diagonal action of G on the left. So for f of something, of a set, so what should I take if I want to get this thing? I should just take the set modulo G as modulo the action of G. That's what it does. Now, does it satisfy that thing? Things sort of become, yeah, so what is it? So F is Q admissible. It becomes sort of stupid, right? So you just have, you have just some sets, U and times G and times V, and you take this modulo G. Now, whatever the action of G is on U and V, when it acts here just by left multiplication, then this quotient can be simply identified with U times V. You just embed U times V here as U times 1 times V, and that's a section for this, for deduction. So this is always just that. But who is then this F of U times G is again just U, and F of G times V is just V, and this famous isomorphism is just the identity. Yeah, so it's a very wonderful way how to talk about such a stupid, about the identity, about such a stupid thing, right? So this is the only thing that's happening here. And for the other thing, I could, okay. I guess you can verify that the G mod G is a point, right? So F of Q. It's okay, and that's what you're getting. And finally, so why do we do it? Because we want to construct our Hopf algebra. So theorem. So if how is it D and C are DMCs, Q in the cocommutative coalgebra, F from D to C, a Q admissible functor, then when we take f of the guy of EQ, see, f is commonoidal, so it sends coalgebras to coalgebras, no problem. So this guy who is a simplicial coalgebra or object in C coalg. So this guy is actually the nerve of a bialgebra. H, well, who is necessarily F E2Q. This means that's F Q in C. So we constructed once we have it, we have a bialgebra, and as here one can imagine, well, it's not just a monoid but a group, so the same thing should be happening here. It shouldn't be just a bialgebra but a Hopf algebra, and indeed. So and finally, I can say that there is also an antipode so and S, which is whom? Well, S should be S should be somebody going from H to H. And who's that going to be? S is F of beta QQ. You see, because like this H, that's F Q tensor Q. So I just exchange those two things, apply F, and apply, get S. So that thing is an antipode on the H. In particular, that antipode is invertible. Just because since beta is invertible. Okay, so there is our Hopf algebra. Possibly those definitions are a little bit long, but it's just this. We really just do that stuff in some non-commutative sense. This EG gets replaced by this Khobar construction of somebody who is like replacement of a set, here a co-commutative coalgebra. And then we need to talk about this mod G stuff, so which should be some functor that kills one of those Qs. Okay, so that's it. So let me try to prove it. Or, yeah, that's still 10 minutes, so let me write this before the proof. So, since that's sort of a theorem where we finally construct a Hopf algebra, so let's just maybe write down explicitly what that Hopf algebra is. Then who cares about some proof, that just to have some hands-on understanding of what precisely is that Hopf algebra that we constructed. So what is H? So first of all, this H is F of QQ. It's fine. Now, what is the coproduct? on H. It's supposed to be bi-algebra, so there should be product and coproduct. So the coproduct simply, it's as a coalgebra, it simply inherits the coalgebra structure on Q tensor Q. So it's the thing that I just erased at some point. So you take 2 copies of Q, you take the coproduct in Q, and then, so this goes from QQ to QQQQ, but then you want to go back to, down to F, down to H, so apply F here. Now you would apply F there, you would get F of QQQQ, but instead of that, well, you still apply this comonoidal structure, because you want to go down to F of QQ, tensor F of QQ. That's it. That's the coproduct. It's reasonable. With co-unit is the same stuff. You might simply take F of epsilon tensor epsilon, if you wish. So we start with QQ, then apply the co-unit, end up with the unit object. So we get F from here. Now we land here in F of 1, and then from here we can go to 1 in D to 1 in C. Or equivalently, what we can do, it's probably enough to apply the co-unit once. So we can just take F of QQ. So we apply the co-unit, then we get this guy, which is, so we go to F of Q. But we understood that this thing is actually isomorphic with 1 when this isomorphism is exactly given by applying co-unit. So just as long as you remember that in being Q admissible requires that there is some particular thing is an isomorphism between 1 in C and F of Q, then this guy is also the co-unit on our H. Okay. But anyway, who cares about co-unit? The coproduct is more interesting. And also the product is pretty interesting. So how should I write it with the product? Like this, okay. So we just take this F of E2Q, which is F of Q, Q, Q. And now remember, this being admissible implied that this guy is isomorphic to FQQ tensor FQQ. This is this admissible. You just split this Q here in the middle.
So is it E3 of Q at the beginning?
It's E2. It's like you imagine that it's like this. There are 2 of those, or there's things are called 0, 1, 2. That's why there are 3. And this the number is 2, so it's.
So in the in theorem, okay.
So it's like this, and now from here we can go to E1Q, so it's just FQQ. And how do we get there? This is what corresponds to that picture, right? So we have that thing, this thing, and then we take this map going from 1 to 2. So what do we do with E? Do you remember, if there is somebody who's not connected with anybody, we need to kill it with epsilon. Everybody who's connected just stays. Possibly if it's connected with several things, we apply coproduct. So the map coming this way is like F of identity tensor epsilon tensor identity. That's it. And it's cool because now, okay, this is isomorphic. We have a map. That's the product. In H. There we are. And okay, so let me now prove it. Proof of, did I call it a theorem, this theorem, or did I call it a proposition, that proposition? The last thing. Theorem. Proof of the so we just need to verify that f of EQ is the nerve of a bialgebra. And so what should we do for that? So we take f of E k plus L Q. We know this recognition proposition which says how to do it. So we just take a thing like this. So that's what that's f Q power k times Q times Q power L. Now we know that this is isomorphic, or let me maybe write it as a sequence. So that goes to, or let me not write it as a sequence. So this is isomorphic to f Q power k times Q times f Q power L. What we're using here, we're using this thing that f is admissible, right? That we just split this Q in the middle. And that thing is nothing but f of EKQ tensor f of ELQ. Very well, right? So we get an isomorphism between this and that. Isomorphism in C. But one still needs to verify that, okay, it's an isomorphism of objects in C, but if you remember that proposition, it says that, well, it's the nerve of a bialgebra if and only if this map is an isomorphism of coalgebras. And okay, I'm sort of out of time, so what I'll tell you. So one needs to verify this is a morphism of coalgebras, that one can exchange with the coproduct, so to say. So that's where, to do it, one just uses, again, some commutativity. So it is because F is braided comonoidal. So far, we never used the fact that it's actually braided, but here, if it's somehow commutative enough in some sense, then this guy will preserve the coproduct, and let's call this an exercise. And let's make it to an actual exercise then. And okay, so this implies that we actually do have a do have a bialgebra, and then one simply verifies that S is an antipode, and so the rest is, at least for the moment, unless I change my mind, is also an exercise. Okay. So that's the end of this horrible formal part about constructing of Hopf algebras. But at least those formulas, they don't look that bad. And finally, next time we'll quantize those Poissonic groups, and that will be the end. And then after that, we'll probably have a cake, right? I'm not sure what to do with the last week. Okay, thanks.